Today we are going to talk about exponential growth some more. Yesterday we looked at how to graph exponential growth functions. Today we're going to look at some applications of exponential growth. So it's when a real-life quantity increases by a fixed percent each given time period, and we could be talking about days, weeks, months, years, hours, whatever. That would be considered an exponential growth situation. So if something increases by, let's say, 50% each year. Let's say I begin with 100. After 1 year, how much will I have? 150. Then after the next year, how much will I have? 225. So we take half of what we currently have and add that on every time. So it's not just half of whatever you initially started and you do the same thing every time, but you're doing half of what you currently have each time period and adding that on. That would be an exponential growth, okay, when we have the same rate of growth every year. Our formula is given down at the bottom, does not need to be memorized, but it does have a slight error in it here. We need to have an A in front of there. That A is the initial amount. That's how much we're starting with. So like when I said we start with 100. R is the rate of increase, and that rate is as a percent. So when we put it into the formula, we'll need to put it in as a decimal number, not as the percentage value. And then T is the amount of time periods measured in whatever type of time period we're measuring in, but the amount of those time periods. Some more vocabulary with this that your homework will ask you about. The growth factor is that entire middle part, the base. The base is the growth factor. And then it will ask you for the rate of increase. The rate of increase is just that percentage part of it. Okay, so the growth factor is the entire base. The rate of increase would just be the percentage part of that, not the one. So we're going to use that formula to solve some questions. In January 1993, there were about 1.313 million internet hosts. During the next 5 years, the number of hosts increased by about 100% per year. Write a model giving a number h in millions of hosts t years after 1993. When a problem asks you to write a model, that is an equation with two variables in it. A lot of students try to plug in too much stuff. Okay? A model should be an equation that has two variables in it. So we're going to use that formula. Y is equal to a 1 plus r to the t. This question says giving the number h, because we're talking about hosts, sometimes we like to, instead of just always calling it y, give it some sort of a meaning. So they said let's call it h since it stands for hosts. Initial amount is 1.313 because it says in millions. So we're going to turn that number into a more manageable size instead of having to worry about all of those zeros. Times 1 plus. What is the rate? 100%, and how will that go into the equation? As 1. So when we plug it into the equation, we want to turn that percent value into a decimal. And then t remains t for the model. Don't plug anything in for t.
Could we just write the equation as 1.313 in parentheses 2?
Yes. So then to clean it up, we're going to finish out by saying h is equal to 1.313 times 2 to the t. And if you skip that little intermediate step, since we're just adding 1, that's something you can probably do in your head. So that's fine. You don't have to show your work of that middle step. I just show my work because if I don't, then students will ask me where something came from, and then I'll have to go back and show it anyway. All right, so that's our model. That first part actually asks us two questions, though, because it says write a model, and then it says about how many hosts were there in 1996. So what would I do to find that? Plug in a 3 for t. Why are we plugging in 3 and not 1996? Because it's been 3 years since the beginning of our measurement. So we know that at 1993, we had 1.313. So we want to know 3 years later. Okay, so t is the amount of time that has passed since the initial value. Do not plug in 1996. I don't even think your calculator will do that. It's so ridiculously large. So we're going to do 1.313 times 2 to the third. And we get about 10.5. Questions on that part? Part B then wants us to graph this. To graph it, we're going to use XY charts like yesterday, but unlike yesterday, we are only going to really be caring about positive values because we're not going to be concerned with negative time. We don't want to know what happened before 1993. And negative internet hosts doesn't make sense. So in our problems for applications, we're only going to be considered with our first quadrant region. So you can just put your axes right along the edge, and that gives you more room to graph. We're going to graph that equation that we found in the first part. So that was y is equal, or h is equal to 1.313 times 2 to the t. And we're going to make an xy chart, or in this case, a th chart. We already know two values. We know that initially we had 1.313. And we know that after 3 years, we had 10.5. So we already actually know two values. You can pick any numbers for t that you want. So I'm going to let part C guide me on what might be helpful. Part C says, use the graph to estimate when there were 30 million hosts. So my goal is I want to get that h close to 30 so that I'll be able to answer part C well. So 3 didn't get us there. Maybe 5 will do it. So I'm going to plug a 5 into the equation. That takes us to 42. Okay, so we overshot. So it must be that it's actually back by 4. So we'll plug in a 4. And I get 21. So it must be that it was between 4 and 5. Okay, so a few points to plot is good. And then we can plot those on our x and y axis, or in this case, each axis. Time is always your x-axis, and we'll just count that by ones. If I have to go all the way up to 42, counting by ones does not seem like a good idea, so I'll maybe count by 4 there on my y-axis. And it's okay to count by different things. So then I plot the points, remembering my scaling. And then connect the dots. So we get a graph like we had yesterday. To answer part C again, it said, in what year were there about 30 million hosts? So it was sometime between year 4 and year 5. So what would our answer be for that? 1997, because we began at 1993, so if I'm 4 and a bit years later, I would be sometime in mid to late 1997. Okay, so make sure you answer the question that's asked. If it says how many years later, then you can just give the number from the chart. But if it says in what year, then we're talking about a calendar year. So you need to add that to your starting year. Questions?
get that one dot to be perfectly on it?
It's 21, so I guess it should have maybe been a little bit above.
I was just wondering.
Yeah. I didn't plot perfect there.
I have a quick question.
Sure.
On the last problem, why did you start with 3 as t?
Because we had already plugged in 3 for part A, so I was just stealing a point that we already knew.
I mean, why did you do it for part A?
Oh, because it was asking about 1996, which is 3 years past 1993.
Oh.
So in this one, 1990, state tuition is $4,300. During the next 8 years, tuition rose 4% each year. When it gives that parameter of during the next 8 years, and the last question said during the next 5 years, what that means is this model is really only a good predictor for a certain amount of time. So with our internet problem, for 5 years, they were growing at 100% every year, but then the internet was probably pretty built up, and that pace slowed down some. So when it gives that parameter, it means if we use this model to guesstimate anything further out than that, it's probably not going to be very accurate. Okay, so we don't actually apply it into the solving, but it's more like a warning of this problem, this equation will only work for so long. Okay. So during the next 8 years, tuition rose 4% each year. So write a model. So we're going to have tuition Y is A. What's A? 4,300 initial amount. 1 plus rate. What's rate? 0.04, 4% as a decimal, to the power of t. In our model, we want t to just be t. We're not plugging anything in for it. So we can simplify that by in the middle adding it up and making it 1.04 to the t. So using those terms again that we talked about on the first slide, in this equation, the growth factor would be 1.04. The percent increase would be 4%. Okay, so from the equation, we can get our growth factor. It's just the whole base. And then the percent increase is the not one part of the base. Okay. Okay, then that's all part A asks us to do, is to just write the model. So then we're ready to graph for part B. Once again, we're not going to care about negative dollars because most colleges are not going to pay you to go there. And we're not going to worry about going back in time. So our equation was 4,300, 1.04 to the t. Oops. And so we're going to create an XY chart again, letting part C guide us. So what does part C say?
Like in what year did the tuition reach 6 grand?
In what year did it cost $6,000 to go to school? So we are going to pick values based on trying to get this up to 6,000. So well, we know 0 is 4,300. So that's one value that we're just given. That's our initial. 4% is not very much. So I'm thinking this might take a while to get there. So I'm going to say maybe it's 5 years. Try plugging in 5. That is 52.31. Okay, so 5 years doesn't cut it. Maybe 8 years will do it then. $5,884. Not quite, so maybe it's 9. And that gives us the 6120. When you choose points, if you are a very good guesser and you happen to get just the right answer on the second point, please still plot more than just the 2 points. Okay? We want at least 3 points on our graph to be able to get a good accurate curve shape to it. If we just have 2 points, our graphs pretty much start to look like straight lines. So get at least 3 points that we can see a nice curve to it. 4 is even better. Now when we graph this, we have some options. On our x-axis, we'll just count by ones because we only need to go out to 9, so that's not a big deal. But on the y-axis, we have to go all the way up to 6,000. So one option would be to count by something pretty big so that we could fit everything in. Another option, which is something that they really love to do on standardized tests a lot, is actually break part of the graph out and then start counting at a different value. So when we see this little symbol on an axis, what that means is there was nothing going on in that space, so we're just kind of erasing that part out, and then you can start counting at whatever you want. So I'll start counting at 4,000 right past that little cutout, and then I could count by something smaller than what I would have to count by if I wanted to actually show all that empty space. So we'll count by 400s. We could have even counted by something smaller and still been able to fit it in. So our point 0 is at 4,300. At 8, we are up to 58. And at 9, we are just past the 6. That's not a very curved graph. Why do you think that is?
Because 4% is
4% is not a big increase. So yesterday we talked about how the bigger the base value is, or today we're calling that our growth factor, the more curved the graph will be, the stronger of a turn it's going to take. So in our last problem, 100% gave us a base of 2, and we saw a really sharp turn there. Whereas a 4%, 1.04, that's hardly growth at all. If our base was just 1, that would mean tuition was not increasing. It was just the same every year. So this is not that much bigger than 1, so we're not seeing that much of an increase. Okay? So if you have a small growth factor value, expect it to be a pretty linear graph. Part CS, in what year did tuition reach 6,000? So what would we say? 98, 99. Probably I'd go with 99 because usually tuition increases don't happen like in the middle of a semester. Right, they kind of wait. But I would accept 98 or 99 because it happens somewhere between the 8th and the 9th year. Okay. Questions on that? Our other application we're going to look at today is compound interest, which deals with money, and students tend to like math if it talks about money. That seems like a good reason to talk about math. So when you put money in a bank, banks are actually really nice. What they do is they say, if you put your money here, we will actually give you some money. They call that interest. And the amount of money that they give you is based on how much you put in there. But then they're actually so nice that what happens is you put your money in the bank for a while and then they give you some interest. Then the next time they give you interest, they not only give you the interest based off of what you originally put in there, but on the money they gave you. So they're giving money off of money they already gave you. And this is what we call compound interest, where that interest is going to grow on itself too. So when that happens, we get this equation, which is pretty messy, but you don't need to memorize it. P stands for principal. That's our starting amount of money. That's how much money we put in the bank at the get-go. R is our rate, and again, we'll want that as a decimal. N is the number of compound times in 1 year. So banks can differ on this. Some of them will give you money every quarter. Some of them will calculate. Some of it could only do it once a year. So N is the number of times that they calculate that interest in a year. And then T is the number of years that you leave your money sitting there. So in this problem, we're going to deposit $1,000. That's our principal. Into an account that pays 8% interest. That's our rate. Good luck with that. 8 is extremely unrealistic. The highest I've ever seen is Lake Michigan does 3.5. That's really high, a lot higher than any other banks. So 8% is kind of ridiculous, but that's the number the book gave us, so we'll go with it. Find the balance after 1 year, so that's our time, if interest is compounded with the given frequency. So this is like a part A, B, and C question. So part A says annually. If they give us interest annually, how many times a year are they giving us interest? Once, and that's our N value in the formula. So we're going to plug this stuff into that formula. Amount equals principal times 1 plus rate as a decimal divided by N to the power of N times T. A suggestion for calculating this. In your calculator, the first thing I would figure out is the exponent. Okay, 1 times 1. We don't really need our calculator for this one. But if we were doing it, say, daily, 365 for 5 years, I don't know what that is in my head. So the first thing I would calculate is whatever that exponent is going to be. Then the next thing I would calculate would be what this base is going to be. And then into my calculator, I would type 1,000 times whatever answer I got there to the power of whatever answer I got for that other one. Do not do any rounding through the process of the question. Use the fact that your calculator has that A and S thing and will base on previous answers. If you round in the middle of the calculations, it will make a big difference in your final answer. Okay, so do not do any rounding in the process of the problem. For this one, when we plug everything in, we get 1,080. So this question asks for the balance after 1 year, so our balance would be 1,080. If they ask how much interest did you earn, what would our answer be? $80, because that's the amount of money that's different than what we started with. Okay? So $80 free for just letting our money sit there. It's a pretty good deal. Part B says, what about if instead they gave it to us quarterly? How many times a year would that be? 4. So we're going to have A equals 1,000, 1 plus 0.08 divided by 4 to the power of 4 times 1. What happens is they don't give you 8% every time they give you money. They give you 8% over the course of the year. So that's why we're taking that rate and dividing it by us. So they're really only giving us 2% each time they give us the money, but it'll work out to 8% over the course of the year. Yes?
Why would they do that instead of just giving you $80 every year instead of giving you 20?
It's not going to be 20 every quarter. So when we type this all in,
Oh, is it going to be
we get, let's see, $1,082.43. Because what happens is, after that first quarter, they give you some money. Then when they figure it the next quarter, they figure it based on the 1,000 you put in and the money they gave you. So we have a bigger balance there to figure our money off of. So the more times we compound in a year, the better off it's going to be for us. Okay? You will earn more interest if your bank compounds more frequently, because then every time they figure interest, they're figuring it also on including the last stuff they gave you. So it turned out a little bit better. I mean, 243, that won't even take me to Starbucks, but it's a little bit better. And that's just 1 year. If we left it in there longer, it would do more for us. And then for the last part, it's daily. We're going to use 365 for daily, even though it's like 365 and a quarter. We could consider leap years or whatever, but let's do 365. So 1,000, 1 plus 0.08 over 365 to the 365 times 1. And this is where if we were talking about more than 1 year, I would definitely need to calculate that exponent as the first thing I would do. And this gives us 1083.277. So banks are nice enough to give us interest, but they are not nice enough to round up. Banks always round down. So they'll give us $3.27, but not $3.28. So. All right. Questions? The last example is really the same, except we have one new type of category here. Semi-annually would be what? 2, twice a year. Okay, semi-annually is twice a year after every half year is what the semi means, a half year. So that would be twice in a year. Another one that could come up would be monthly, so we would have 12. But other than that, the process of the problem is the same, so I think we'll just skip it and go on to your homework, which is in 8.1 again.